So I gave you some background related to Spark. Then I gave you some background related to Spark programming. And then also we talk about Kafka queuing or messaging system. Now we are at the final leg where we'll talk about Apache Spark Streaming. That will complete the full-fledged of the how we can process the window-based stream data analytics using Spark and Kafka. And then I hope you will be ready for your hands-on lab 2 or lab 3. So first I will introduce you what is the data stream, what does a data stream mean, and then what Spark can provide in terms of the streaming. Then I will introduce you some of the streaming features. One important feature is called dstream, and then we will show you some examples. And then after that, I think you will be ready to process the text news articles in a streaming manner. You can process it and then classify it. So what is data stream? Data stream is a continuous flow of data. So sensor network, call center records, social media, from there we generate humongous amount of streaming data because data are continuously coming or evolving. Streaming data device continuously flowing input data into a discrete unit of processing. So now just think about this. You have a network traffic. Network traffic comes in terms of the packet, right? The packet has a header and the payload, right? And then here you have a firewall rule. Firewall rule will tell you that if the traffic comes from a particular IP, block it. If source is particular IP or target particular port, block that traffic, something like this. Now, even if the traffic passes the firewall, there is no guarantee that traffic will be benign. It might be malicious and so on. So, but the point I'm trying to make here, this network traffic is an example of stream data because these data are continuously coming one after another. So now, if I need to process this data, where I can process it? I need to run some analytics algorithm after this. So one possible solution is data are coming, let's think about with a very high speed. What I will deploy Kafka system for buffering or messaging, and then I will run some streaming analytics algorithm here to identify whether incoming traffic is benign or malicious. If it is benign, then it will go to the server. If it is malicious, then I will do further analysis. So now in a Spark, I said we divide this incoming traffic. So is a flow of information, one after another is coming. So one way I can divide the data into a micro batch. And this micro batch you can think about as a chunk. So one way you can divide the data into a micro batch or chunk. So first 1,000 instance will form one chunk, second 1,000 instance will form another chunk, third chunk in 1,000 instance will form the third chunk, something like this. But with this type of number of instance control, the chunk size will be equal. Each chunk will accommodate 1,000 instances, data points. But there is a possibility that some of the traffic packets may come very quickly, and then all on a sudden there may not be any traffic, and then after that traffic may start. So that way, this approach may suffer something. So this approach may not work very well. So that's why in Spark streaming, the chunk is defined not in terms of the instances. The chunk boundary will not be defined in terms of instances. Chunk boundary will be defined in terms of the time interval. Okay, so So that's why I said flowing input data into discrete units for processing, that we call it micro batch. And data stream is a technique for transferring data so that it can be processed as a steady and continuous stream. Streaming technologies are becoming increasingly important now. So where it can be applied? It can be applied in fraud detection, it can be applied in intrusion detection, and it can be applied malware detection in network traffic, even for personalized advertisement and so on. We'll show you an application in tomorrow where we can do the anomaly detection on the IoT data. So in tomorrow we'll show you a sensor or IoT device will give you some readings. So every 5 minutes, or in our case every 5 minutes, but you can configure it every second. You can get the data. In this case, data will come, the IoT device will capture the temperature, humidity, and other properties. So it will give you 4 readings like the humidity, temperature, and so on. So our goal is to identify from there whether we can observe in any anomaly or not. So in that case, let's say the sensor or IoT device was deployed in outside environment, and there is a windy situation. In that case, you can say that might be an anomaly, right? So our goal is to detect those type of anomaly in real time. So that we will demonstrate you tomorrow. But the point I'm trying to make, this data will be, the sensor will generate humongous amount of data, and those data are continuously coming, and we want to do the anomaly detection in real time. So similarly, in network traffic, when the packet comes, I want to determine incoming packet has any malicious content or not, so we want to apply the stream analytics there. The streaming, this is an example of the stream analytics. Now, what is Spark streaming? So I said Spark, most of the Hadoop MapReduce, the criticism for Hadoop MapReduce is good for batch processing, is not good for online or stream processing. On the other hand, Spark is good for not only for batch processing, it is also good for stream processing. And there they use the idea I will explain. I try to explain it here, so I will go through again. So it was extension of the core Spark technology. It provides you high throughput fault tolerance for the stream, even for the stream processing. It can handle the live streaming data. And it supports data sources like HDFS directory, TCP socket, Kafka, Flume, Twitters, and so on. So what I said, so for example, you can just think about Kafka is a messaging system that will connect with the source or producer. Producer will produce the messages that you already said, and then it will, in the Kafka will handle that message by keeping it in the partition and so on. And then Kafka will push that message to the consumer. Basically, consumer will pull the message from the Kafka. So in this case, consumer will be the Spark streaming framework. So it will read the data from this input data stream, and then Spark streaming will start to construct micro batch. So in this case, micro batch will be basically a window, and each window can be, say, 1 second, or it is configurable. And within that window, basically it will consist of a number of records, and from there we will construct some RDD. And then Spark engine will work on that RDD and produce some output that will go to the HDFS. So the key point I'm trying to make here, again, so data are continuously coming. So every X second, so X is configurable. Let's say X is 1 second in my example. So first 1 second, it will form a chunk, or we call it formally D stream. So a sequence of D stream consists of a sequence of micro batch. So each micro batch in this case will be, each micro batch will consist of a, in time interval or the chunk interval will be the x time unit or x second. So in that case, let's say x equal to 1 second. So in that 1 second, whatever the data we will get, we will apply the RDD operations and produce some output. And then that will be the input for the next steps and so on. So here, just think about, so we chop it into, let's say, 3 micro batches. Batch 1, batch 2, batch 3. Or you can say batch at t, batch at t plus 1, batch at t plus 2. And in this case, the x equal to 1 time unit. So now each of these batch will be fed into the Spark engine, and Spark, each micro batch will consist of what? It consists of a number of records. It may be first batch, micro batch may have 50 records. Second micro batch may have 100 records. Third micro batch may have only 10 records. And then each of these micro batch Spark engine wants to process and produce RDD. So from the Spark perspective, it will see as a number of records and apply the RDD operations on it. So here the advantage of this Spark streaming, this micro batch, whatever the records we have there are very few records will be there. So easily it can feed into one machine's main memory. So here in a previous Spark context, when you have a batch data or offline data, so we usually keep it, when RDD is created, there is a possibility that RDD may be stored in the disk. But in this case, the RDD we are creating here for the micro batch, those RDD will be stored into the main memory. Furthermore, this RDD may be replicated multiple times in many machines' main memory. So let's say first batch 1, a batch at T, we will process it here, and RDD has been created. That RDD, let's say batch at T, we will chop it, and a batch at T will be processed here. That batch at T will be replicated into the more than one machine's main memory. So let's say this is machine's M1, and it will be also replicated in machine's M5 due to the facilitated fault tolerance. Because all on a sudden, machine's M1 may fail. If machine M1 is failing, then what will happen? We need to start that micro batch operations, the Spark RDD operation in somewhere else. So that's why this micro batch content will be replicated across more than one machine's main memory.
Is that Spark engine one process or is it across several?
Okay, so it has a Spark maintains, it doesn't fall like Hadoop MapReduce has a master-slave architecture, but here we have many nodes. So those nodes will serve as a, you can say as a, it's not exactly master-slave, but yeah, there will be a driver program, and then the rest of the nodes will serve as a processing node, and those or rest of machines will serve as a processing node. They can work in parallel. And right, worker node. So each worker node will have more than one task can be run based on your number of cores. So each machine has a many CPU cores. So those, if you have let's say 4 CPU core, you can run 4 tasks in parallel, for example. Okay, so micro batching is a core Spark technique that lets a task to or process handle a stream as a sequence containing data chunks or small batches. In case of incoming streams, events can be packed into various small batches and then delivered for processing to a batch system. Okay, now one important point is when a Spark driver wants to launch this micro batch processing, so every time when the record comes, it will go to the, it will be first go, in order to facilitate the fault tolerance, it will be written into the using the write ahead log. It will be stored somewhere on the the log, and then it will be available for the micro batching. And another important concept here is, so just think about the Spark streaming is getting the data at this point, and then it will be, so then it will be moved to the, in this case, this source and sink is a little bit different from the, what I'm talking about, the Kafka. So here, the idea is the Spark streaming framework will receive the data, right? And then it starts to come up with the micro batch. So at that time, these are the records will be available for micro batch processing. So there is a delay between when it is available at the Spark streaming framework, and then when it is ready from the framework as a macro batch. So just think about this picture. So what I'm saying here, the data comes from those sources, and it is entering the Spark streaming framework, right? So now the framework will produce the batches. So from here to here, there is some delays involved, because when the data is available immediately, it will be, due to the fault tolerance, it will be replicated, and in some cases, if you have used write-ahead log, it may be persistent on the disk also. And then it will be available for the micro batching. So this delay will be shown by this diagram here. So every time data coming, and then we will, so the micro batch, at this point, the micro batch will be created, and it will be ready for the RDD consumption and so on. Okay, so the important point here in this case is this. The Spark streaming uses new architecture called dstream that I will define now dstream. So Spark streaming can easily scalable to hundreds of nodes, and Spark streaming achieves low latency. It can achieve latency as low as few hundred milliseconds. And it can be, the Spark framework, the beauty is it can do both. It can do batch and real-time processing, or provides the Spark real-time analytics and so on. And Spark interoperability extends to rich library like mlib, can work also on the Spark streaming framework, and it supports SQL, also data frames for the streaming data, and GraphX. And RDD generated by dstream can be converted into the data frames and query it with SQL. So these are the interoperability support you have. So again, the dstream, just think about a contiguous number of micro batches, and each micro batch will contain a number of packets or number of data points. And here I just try to say how the fault tolerance will be taken place in case of for Spark. Spark has the ability to efficiently recover from failures. So let's say here we're doing some micro batching and some RDD operations, and all on a sudden this node is failing. Then we know that the copy of this micro batch is also, we have another copy somewhere here. So then there the job will be launched, and then this recovery will be taken place. So the key point is batches of input data will be replicated in memory for fault tolerance. So the one important key point here is, in the past for fault tolerance, how do you do the fault tolerance in the past for Spark? For Hadoop, MapReduce, the fault tolerance will be taken care by doing the replication. In a Spark, fault tolerance will be taken care by what? By lineage graph. By lineage graph, right? And in this case, streaming case, we don't use, you can say we keep track of the lineage graph, but The main idea is since the data will be stored into the main memory, we keep more than one machine's main memory, we keep the copies. So that way, if one machine is failing, the process will be started to run in a different machines where the data will be local. Data lost due to the worker failures can be recomputed from the replicated input data from the other machines. So that's the idea. So by replication, we will take care of the fault tolerance. But in this case, the replication will be taken place at the main memory level. In Hadoop MapReduce, replication was taken place via disk or a HDFS files block. Okay, now let's go back to the D stream. So we're streaming computation as a series of very small deterministic batch job. So live data stream are coming. So we batch them of X second. X second can be configurable, 1, 2 seconds, and so on. So in that case, it will produce a bunch of micro batches. So chop up live stream into batches of X second. Spark trees each batch of RDD. Spark treats each batch of data as RDD and process them using RDD operations. Finally, the process results of RDD operations are returned in batches. So here, more details what I try to say. So this D stream is called discretized stream, is a basic abstraction provided by the Spark streaming. It represents a continuous stream of data. The input data stream received, it represents continuous stream of data, either the input data stream received from the source or the process data stream generated by transforming the input stream. So here input D stream, it comes from, let's say, from the Kafka, and in that case, you will create an RDD at time 1, RDD at time 2, RDD at time 3, RDD at time 4. So internally, D stream is represented by a continuous series of RDD, and each RDD contains data from a certain interval. So basically, it's a micro batch, and each micro batch will be represented by RDD, contains a number of records. That I try to tell you. And then input D stream, just think about D streams representing input D stream are representing the stream of input data received from streaming sources, like it can be a Kafka, or it can be a Twitter stream, something like this. And the key point is the object stores the data received from a source in the memory of a Spark for processing. And here are some 2 categories of building streaming sources. Basic source can be file system and socket connection. Advanced source can be Kafka, Flume. And then here I just showed you some examples. This example is taken from the Databricks website. So here get the hashtag from the tweeters. So we will get the Twitter streams, and this RDD will be created like this: batch at T, batch at T plus 1, batch at T plus 2. And then from there we create this tweets. We create a apply the flat map. It will create a new D stream called hashtag new D stream will be created. And then from there we can save it into the Hadoop file system. And then for fault tolerance, as I told you before, RDDs are, remember, the sequence of operation that created from its original fault tolerant input data. So that way the lineage graph is constructed in the past. So here we are saying batches of input data will be replicated in memory of multiple worker nodes. So a micro batch will be replicated in more than one machine's main memory. That's the key point. If data is lost in one worker, then it will be started, the process will be started at a different worker. So do you have any questions so far? No? So, and you also know that RDD supports transformation action operations. Those can be applied also. And the D stream sequence of RDD, so this way the input D stream will be created, and the transformation modify data from one D stream to another. So you can apply map, count by value, reduce, all of this operation. And there is a new operation, stateful operations. I will talk about that in a minute. So that can be applied. And then there is a one output operation for each, do everything on with each batch of results. So here we have some transformation operations on the D stream. So map operations is very similar what we did in the past. In the past we do, we take the list or the RDD and apply the map operation and produce a new RDD. So here we said returns a new D stream by passing each element of the source D stream through a function fe1c. And then flat map, the difference is one to many. In the flat map case, for each element, when you apply the function, in the map case, it will produce one element, but in flat map case, instead of one element, it may produce 0 or many elements. And filter will be the returns a new D stream by selecting only the records of the source D stream, which the function is true. And then reduce will return a new D stream of single element RDD by aggregating the elements of each RDD of the source stream using a function fe1c. So these are the things are basically what you learned previously. This transformation over the non-stream data, same thing can be applied, but here the input will be the D stream. Then we have other operations like this. And then window operations can be carried out. Spark Streaming also supports window operation that helps to implement transformation over a window of data that is sliding. So in this case, let's say window size is 3, and then sliding, it will be shifted by 2. So first the window will capture the data from this place to this place, and then it will be shifted by 2 from this place to this place. Each time a window is sliding over a D stream source, the RDD source falling within the particular window are being united. They are then being operated from producing window D stream RDD. So here, for window operation, we have to specify 2 parameters. One is the window length, the duration of the window, and sliding window, the interval at which the window operation is performed. In our figure, it was window length is 3 and the sliding interval is 2. So here are the window operations on the D stream. So here we take the window length and the slide interval. That way we define the window. Returns a new D stream which is computed based on the window batches of the source. And count by window returns a sliding window count of elements in the stream. How many elements are there? So reduce by is a reduce operation, but within the by window. And reduce by key, the difference between these two, here we don't do by the key. Here we are doing by key in a window. So let's say here is an example I tried to say. Window length is 30 and sliding interval 10. So we will create a window, stream.window 30, 10, and then we want to count. So in that case, count of elements in the stream 1 by this. And then we can say reduce by window. So how many elements we have in the number stream, so we can count that by doing this. So here we are saying by this window we want to know window operation is defined here. Window length is 10 and the sliding interval will be 1, and we want to see how many values are there. Now internally there will be efficient implementation for this. So what we do, let's say so here the window will be shifted by 1, right? So sliding interval is this at the beginning, let's say, and it produced some result here. Take count by value, how many, and then it will be shifted by 1. So the new window will be something like this. It will start from here to here. Now one way you can do from the scratch, you can get all of this count and aggregate them. Instead of doing that, what we will do, whatever the results we have, that will be subtracted from this result, and the new result will be added. So this efficient way they implement this. So that we said, here, so the new result, new count will be added with the previous result, and the previous, this part will be subtracted. And so this is the, okay, so this is our previous result, that will be added with the new result, so will be subtracted with the only this part. So that way internally they implement this. And then mlib machine learning so we said mlib machine learning library, I told you a little bit. So that can also be integrated with the Spark streaming context. There is streaming machine learning algorithms which can simultaneously learn from the streaming data as well apply the models. So linear regression, k-means, classification, all of this can be applied here. So in your lab, I think the lab number 3 or demo hands-on number 3, there you will build the model. The classifier will be built from the historical data. So basically we crawl a bunch of news articles offline and build our classifier or model, and then deploy it in the streaming context when the data, we'll crawl the new records every 5 minutes and then try to classify those records based on the model we built offline. Okay, so and now Salam will explain to you the Rafi. So he will explain to you this code more details, and then we will start the hands-on part more details.
So for this part of the session, we will be focusing on an example that will do the count on the number of words that has been coming through the articles, coming from the articles that published through Kafka Producer. So we have to use the streaming context provided by the Apache Spark framework library, and we will create a local streaming context with 2 execution threads. I mean, there will be 2 2 cores of your machine will be used to do the processing job, and every 1 second the process will go on. So the batch interval is set to 1 second now. So this is the example of the source code we have here. So basically we are importing necessary Spark library, like we will need Spark context, streaming context, and the Kafka utils to create the data stream from Kafka. We also know about the brokers that has been the Kafka server location and the topic name, where we will be getting the new messages from the argument. Now first we have to create this Spark context with specifying that we will be using 2 cores of the available cores in the machine, and we are giving it a name so that we can later see in the logs that this application run in this way, in this manner. Then with the help of the Spark context, we will create the streaming context, and we are setting this value to 1, means every 1 second the processing job will be conducted. After that, we are with the help of Kafka utils, we are creating the stream, specifying the topic and the brokers server. Then we are using a flat map operation on the corresponding stream to generate the words by splitting them with the space. Then we for each of the words we found on the flat map operation, we create a pair with word and count. By default, initially the count is 1 every word. So now you have in the system you have word and count pairs, like if happy comes on a document, it will be like happy, 1. Tester, if it comes in the document, it tester, 1. Then with those pairs you will apply the reduce by key operation, which is in this case word, and it will do the sum of the frequency. So it will count all the 1 and do a sum on that, and you finally get the total number of occurrences for a particular word. Here is a option to see the results on the console window. After that, your program has been set up to be running in the Spark, but you have to call the Spark context start method to initialize and start the processing job from the beginning. Before this call, nothing will happen, and you will await for the termination of the computation, which is most of the time Control-C. Because a Spark streaming application, it will go on until you do not close it. So you will find that every line has been marked with the corresponding aspect they are, corresponding job they are doing. To run this program, you have to first run the Zookeeper server, because you will be using Apache Kafka, and following that you will run the Apache Kafka server. You can create the topic if it is not already there with this command. And this follows. This is just for test, that you can send messages through the Kafka. Now, when you have that source code in this page, you have to do a Spark submit to run this code in Spark cluster or local Spark node. For that, you have to use Spark submit. You can specify additional packages that will be using in the program. In our case, is Spark Streaming Kafka. Path to the file where the program has been written. In our case, it is stream word count.py inside some folder where you put it there, and you have some arguments to pass on. This is the argument that lists the broker, and this is the topic you will be expecting message from. Once you are running, you should be able to see lot of outputs, lot of this console outputs. Whenever you see these outputs at some point of time, you may assume that one processing job has been done at this moment. And this is a way you can see the streaming status from a web browser. If you go to localhost :4040 port /streaming, you should be able to see how Spark streaming is going on and define the statistics related to it. So this is the summary outline of this session. So after completing this one, I am expecting if you have any question, you can ask.
They will run the program.
No, not this one. If they want, they can run, but the similar thing you will encounter in the hands-on session. So you can wait for that, or you can run.